Hello everyone, in this video we are going to introduce the concept of oxidation and reduction in organic chemistry. So in general chemistry, we have already learned a reaction called redox reaction. So in redox reaction, we use this Leo, the lion goes and it help us to understand the reaction that the species, if this species in the reaction lose electron, that species get oxidized. And if the species gain electron or get electron, it gets reduced. So the outcome of the redox reaction is one species, if we are looking at the oxidation numbers, the one got oxidized, meaning that oxidation numbers will go up. And the species that get reduced, the oxidation number will go down. In organic chemistry, we will apply the very similar idea. We are going to look at the oxidation state or the number. But here we are only focusing on carbon. So if through a reaction, the oxidation number of carbon increase, that means that is an oxidation reaction. And if the oxidation number decrease of the carbon, that means that reaction is a reduction. So the next question is, how do we know the oxidation number of carbons in the molecule we are looking at? So the general idea here is we are going to treat all the bonds that connect carbon as ionic bond. So what does that mean? That means when you think about ionic bond breaking, that is the bond breaking hydrolytically, and the more electronegative item will get that pair of electrons that come from the bond. And the less electronegative item will not get any electron around it. So what does that mean? Let's look at one example. So if we start with this molecule, this is your methane, and there are 4 carbon-hydrogen bonds. Compared to carbon with hydrogen, carbon is more electronegative. That meaning all these electrons on this bond right here goes to carbon. Okay, I'm just drawing like this to show you that the carbon now have 8 electrons around it based on the way that we treat the bond to determine the oxidation number. And for carbon, neutral carbon, it will only have 4 electrons. So that means at this moment, this carbon have 4 more electrons that give a -4. That is the oxidation number of the carbon in methane. So let's make it a next case. So we are going to draw this out now. This is ethane. The reason why I draw it in a Lewis structure because I want to show you the bond. So now what we are looking at here is the carbon, both carbon same, connect with 3 hydrogens and 1 carbon. So in this case, carbon-hydrogen bond, if we treat it as ionic bond because they have difference in electronegativity, that electrons goes to carbon. So goes to carbon. And for the middle one right here, this bond, because it's shared between carbon and carbon, so that means they don't have difference in electronegativity, so each of them will get 1. Okay. So that means at this moment, the carbon on the left or the carbon on the right will have 7 electrons. And again, neutral carbon have 4. That means the extra 3 will give you an oxidation number -3 for this case. Now let's look at this one. So now if we have ethane, that is alkane, right? You form a carbon-carbon double bond, and here the degree of unsaturation is 1. And if we are looking at this case, this electron goes to carbon, okay? And in the middle, carbon-carbon, they share 4 electrons, so each of them get a 2. Okay, each of them get 2. And the total number of electrons belong to this carbon in order to determine the oxidation state right here is 6 electrons. And compared to the neutral 4, that's extra 2 more. So for ethane, that carbon have oxidation number -2. Now if we add one more pi bond, that we are going to form acetylene or ethane. In this case, if we are looking at carbon, these 2 electrons goes to the carbon because carbon is more electronegative, and then you have 6 electrons shared between these 2 carbons, so it gets 3 for this one and 3 for the other one, so the total will be 5 electrons in terms of assigned oxidation number. And neutral carbon is 4, that means the oxidation number for the carbon in acetylene is -1. Okay. Now we change things up a little bit. So we still have carbons. And for this carbon, we have OH group. So that is an alcohol. This is ethanol. Okay. And we're going to focus on the carbon on the left. So in this case, what we see, the first is your carbon-oxygen single bond. Oxygen more electronegative. So in this case, these 2 electrons actually goes to oxygen now. So the carbon do not get it. And for this 2, still goes to carbon. This 2 still goes to carbon. And the middle one, carbon get 1. So in this case, what we are counting here is for the left carbon, it have 5 electrons in total. And compared to 4 in neutral, the oxidation state for this carbon in ethanol is also -1 oxidation number. And now if we create a carbon-oxygen double bond, which meaning what we have here, just try this one. If we have, okay, this is your aldehyde. So let's look at this carbon now. So for this carbon, both double bond electrons will go to oxygen. I'm going to use red, go to oxygen, so carbon get none. And when we look at carbon-hydrogen bond, carbon get 2. Carbon get 2, and carbon-carbon bond, carbon get 1. So in total, at this moment, this carbon actually have 3 electrons. And compared to the 4 electrons at neutral, you have 1 less electrons. That gives you a +1 as the oxidation state. And we can make this even more, so that if we have carbon and carbon-carbon bond, carbon-oxygen double bond, now what we're seeing here is these electrons go to oxygen, carbon get none, and carbon-carbon, each bond give carbon 1. So here, carbon only have 2 electrons belong to it in terms of assigned oxidation number, and compared to 4, this here is +2 as oxidation state. And now if we make it even more complicated, more so, and we are going to introduce OH group right on the carbon. So what we are seeing now is all this carbon-oxygen bond, oxygen is more electronegative, draw the electron away, and carbon get none. And here, carbon only get 1 from the carbon-carbon bond. So carbon only have 1 electron based on the oxidation number assignment And compared to 4, now you have positive 3 as oxidation number. The last extreme case is if you see, for example, carbon dioxide. I know it's not an organic compound, but sometimes it's a product of organic compound. In this case, all the 4 bonds that between carbon and oxygen gets all. That meaning the electron around carbon have none. And compared to 4e, 4 electrons for neutral carbon, the oxidation state is positive 4. Okay. So you may ask why we need oxidation number or oxidation state, because that is how you can tell if a reaction is oxidation or reduction. For example, if we start from alkane and we add 2 hydrogens in, that's called hydrogenation. That is addition reaction for alkene. And from here to here, add 2 hydrogens, that oxidation number of carbon decreases from -2 to -3. Because oxidation number decreases, that is a reduction. And if we start from the same ethane, the alkene, and we go this route, we add OH and H, which is hydration. If we are looking at oxidation number -2 to -1, that's an increase in the oxidation number. That means from here to here, that is an oxidation process. So the same happens here if you go from, for example, alcohol, and you find a way to make acetic acid. So if we are looking at -1 oxidation number to +3, that's an increase. That's meaning this process is oxidation process. That meaning you need to have some reagent, that's oxidizing reagent. So that is how we determine if the reaction is oxidation or reduction based on the oxidation numbers. So let's look at one more example. If we have this molecule, and somehow I can make something like this. R group is just an alkyl group. And what type of reaction is this? Is oxidation or reduction or neither? How to determine that? Please pause the video and come back to see your answer. Okay, welcome back. So let's see what happened here. So the starting is a ketone. And for ketone, you have carbon-oxygen double bond. Let's see what is the oxidation number. So oxygen is more electronegative, so those 4 electrons go to oxygen, and carbon-carbon, each carbon gets 1, so 2 electrons in total compared to 4. So that is 2 less, so +2 as oxidation number. And for the right one, even you break the carbon-oxygen double bond, but still you have carbon-oxygen bond, 2 of them, so oxygen gets all. And for the carbon right here, each carbon gets 1 from the bond, so it's 2 electrons goes to the carbon in terms of determining the oxidation state, and compared to 4e, and you still have +2. So there is no change on the oxidation number, meaning it's neither. Okay, neither. Not oxidation nor reduction.